Chapter 15 of the Autobiography of an Electron by Charles R. Gibson. This LibriVox recording is in the public domain. Chapter 15. We Send Messages from the Stars. The Scribe's Note on Chapter 15. It is remarkable that man has been able to discover what the distant stars are made of. Our knowledge concerning the chemistry of the stars has been obtained by means of the spectroscope, in which a beam of light from the star is passed through a glass prism. The result is the well-known image of the coloured spectrum, in which certain well-defined lines appear, according to the distant elements originating the æther waves. The electron explains the whole subject from its own point of view. End of Scribe's Note. It is only within recent times that man has observed that we send messages from the distant stars to this planet. But there is nothing new to us in this proceeding. We have been busy sending these messages ever since the solar system was formed. Through all those ages we have kept on sending these messages, knowing that in time man must come to take notice of them. If the subject should happen to be new to you, you will be anxious to know to what kind of messages I refer. Needless to say, they are wireless messages, waves in the great æther ocean. The waves, to which I refer specially, fall within that small range of which I told you something in the preceding chapter. In other words, they are those waves to which man has given the name light. But what special information do these waves, coming from the stars, convey to man? They tell him of what materials these distant stars are made. Needless to say, it is we electrons who produce those informative waves. You are familiar with our method of producing waves. You know that we whirl around the atoms of matter at prodigious speeds, and that according to the number of revolutions we make per second, we produce waves of corresponding frequencies. In an earlier chapter I have hinted that the speed of the revolving electron is determined by the kind of atom to which it acts as a satellite. For instance, when electrons revolve around iron atoms, they produce certain wave-lengths, while those moving around hydrogen atoms produce an entirely different series of waves. But how is man to recognize these? It is quite evident that man may gaze at a distant star and be little the wiser concerning the different lengths of the waves which impinge upon his eyes. He may observe that the sensation is inclined to red, from which he may infer that the waves are long ones, that they are farther apart than some of the waves produced by a white-hot body. But had man been content to try and decipher our wireless messages in this rough and ready manner, he would never have gained the interesting information which we have now placed in his hands. How, then, did we enable man to read our messages? Our plan may seem to be somewhat mysterious, but I assure you that it is really very simple. When these æther waves of light fall upon a triangular prism of glass, the waves are bent out of their normally straight path. But the point that may seem strange to you is that those waves which produce the sensation of red are not bent so much as the others. The more rapidly the waves follow one another, the greater is the bending of such a ray from its original direction. In this way the various wave-lengths are all spread out, so that they form an image like a coloured ribbon, red at one end being followed by orange, yellow, green, blue, and violet. Every man must be familiar with this coloured spectrum. When some of my fellows are enclosed in drops of water in the air, they produce a great rainbow spectrum across the heavens. But I must tell you how we electrons succeed in bending these rays of light. I have told you already how we either absorb or reflect the æther waves which happen to fall upon us. In most substances it is only those electrons very near the surface that are disturbed. They succeed in stopping the waves. They may do this in either of two different ways. If the satellite electrons are attracted strongly by their atoms, the electrons will spin around the atoms keeping time to the movements of the incoming waves, and in this way the electrons take up the energy of the waves. In doing this the electrons send out fresh waves in the æther. This is the real explanation of what man calls reflection of light. In the second case, the electrons are not so firmly attached to their atoms, so that the incoming waves dislodge them and they are knocked about from atom to atom, and in this way the energy of the waves is frittered away. Man speaks of the light having been absorbed by the substance upon which it fell. In both cases, the only electrons which take part in these actions are those electrons who can move in sympathy with the incoming waves. It will be clear to you that only those of us who are near the surface of a substance know anything about these incoming waves. The electrons attached to atoms in the interior of the substance are left in peace, owing to the defensive actions of our fellows on the outside. But this is not the case with all substances. There are some congregations of atoms through which the æther waves can make their way. Man calls such materials transparent. For example, glass and water are transparent substances. The fact of the matter is that in such substances none of us are able to respond to the incoming waves, and so we cannot stop them. I should say almost none of us, for there are always a few electrons present who happen to be in sympathy with the incoming waves. That is why no substance is perfectly transparent. The point concerning which I wish to speak in particular is this. Although we allow the æther waves to pass through such substances, we do offer some slight resistance to the passage of the waves. The faster the to and fro motion of the waves, the more resistance do we offer. That is why the waves of highest frequency are bent farthest from the straight line when passed through a glass prism. We actually force the æther waves to travel slower through a piece of glass than through the air. Now there should be no mystery concerning our action in a triangular piece of glass. Whatever combination of æther waves falls upon it, the different trains of waves are sorted out according to their frequencies. Suppose, for instance, that æther waves emitted from some incandescent sodium are passed through a glass prism. The bulk of the electrons attached to the sodium atoms are capable of revolving at speeds which produce waves causing the sensation of yellow. Hence there will appear a very distinct line of yellow light in the spectrum. But why should the light be in the form of a line? Simply because our æther waves are passed through a narrow slit in a shutter. But I need not trouble you with further details of our actions, which, although very simple to us, may seem somewhat strange to you. You will understand, however, that we form bright lines in different parts of the spectrum, according to the kinds of atoms to which we are attached. It was this fact which attracted man's attention to our wireless messages. He soon discovered the meaning of these lines, for he commenced to take exact notes of the different positions in which we placed these lines. He saw that when we were attached to hydrogen atoms we always produced 3 prominent lines. A very distinct line in the red section, another in the blue part, and a third one somewhat fainter and farther along in the blue. On the other hand, when attached to sodium atoms, we produced 2 very distinct lines in the yellow. When attached to iron atoms, we produced a great variety of lines in the spectrum. Of course, these substances have to be incandescent to enable us to produce the æther waves. Now it will be clear to you how we send wireless messages from the distant stars. These stars are great masses of flaming gases, so that the satellite electrons are kept busy dancing attendance to excited atoms. The electrons are constantly sending out æther waves, which reach this planet. We sort out these waves when man passes them through a glass prism mounted in a telescope arrangement which he calls a spectroscope. He then examines the positions of the lines we produce in the resulting spectrum, and from these he knows what kinds of atoms are present in the distant star. It is we who have informed man that there are 40 different materials in the sun, the most common of which are hydrogen, sodium, iron, copper, nickel, and zinc. Of course these all exist in a gaseous form. There is one point about which I need hardly trouble you, although it is worth mentioning in passing. While we produce bright lines in the spectrum of any incandescent substance on this planet, our messages from the stars appear as dark lines. The reason for this is that there are cooler masses of the gases surrounding the incandescent masses forming the stars, and these cooler gases completely absorb the waves we produce. So completely are these waves absorbed that blank spaces are left in the spectrum, and these are the dark lines to which I refer. As they are in the same positions that the bright lines would have occupied had the waves reached the earth, it makes no difference to the reading of our messages. Curiously enough, some of our actions in forming lines in the spectrum led to our actual discovery by man, but I shall tell you of this in the following chapter. Chapter 16.